Good morning. So today we will again continue with the analysis of system which we have just started yesterday. So the control volume allows for both mass transfer as well as energy transfers in the terms of heat and work. Basically the reactants come in, flows in, and the product flows out in the control volume. However, if you take a system which is a fixed mass, we have the mass transfer not occurring in this. See, for example, I can have a piston cylinder arrangement, and there may be some reactants inside which upon ignition will convert into product. Similarly, I can also have a constant volume vessel where the reaction can occur. In both the cases, heat transfer is allowed. So here in the first case, the volume can change because the piston can displace itself, so that the volume can change. In the second case, volume is constant. So mass cannot flow in or flow out. So such applications are there in lab scale devices. Okay, see, for example, if you want to find some burning characteristics in a well mixed reactants in a constant pressure environment. So this is normally a constant pressure environment, and here it's a constant volume environment. So if you want to understand the premix combustion of a fuel and air mixture in a constant pressure environment, then we can go for such a device, piston cylinder arrangement, where the piston is free to move up. And in the other hand, the bomb calorimeter type of device where you have a constant volume thing. Even the explosion, pressure rises, etc. can be checked in this. Okay, so in this case, basically the first law of thermodynamics, as we have seen earlier, is written as Q minus W equal to delta E, that is E2 minus E1, the final state energy minus the initial state energy, where E, as I told earlier, is the sum of internal energy U plus kinetic energy plus potential energy, and internal energy basically is a function of temperature, volume, pressure, etc. For ideal gases, this will be a function of temperature only. So the kinetic energy of a system is nothing but the system itself. If it is traveling with the velocity, then it has a kinetic energy. Similarly, the potential of the system also is dependent on the system itself being at a particular height than the reference plane and so on. But in general cases, the changes in the kinetic energy and potential energy are negligible. So the total energy change E2 minus E1 translates as the change in the internal energy U2 minus U1. So you can easily note here that the U1 will be the internal energy of the reactants and U2 will be the internal energy of the products, because reactants are converted into products in both these cases. So Q in the left hand side is the heat interaction. In the case of combustion, the heat is rejected from the system to the surroundings, so it is negative. W basically is there due to the displacement of the volume of the system, which occurs in the first case in the piston cylinder arrangement. So W can be written as integral P dV. In most of the cases, if the piston is free to move and the pressure is remaining constant, then I can write this as P into delta V. So a delta V causes a displacement of the volume that will give you a work interaction between the system and the surrounding. In this case, system does the work on the surroundings. Heat is transferred from the system to surroundings in the case of exothermic reaction, and it is rejected to the surroundings. Okay, so the internal energy change U2 minus U1 is nothing but the U of products minus U of reactants. Now, let us consider the reaction at constant pressure where the piston has forces from two sides. The internal reactant or the product mixture will give some pressure. Similarly, atmospheric pressure and whatever be the weight of the piston etc. can give the external force. If these two are not balanced, then the piston will try to rise up and maintain the pressure constant. Okay, so the movement of the piston, if the piston is locked, then pressure will rise, volume will be constant, but in this case piston can rise up and pressure is maintained constant. So, as I told you, Q minus W is written as P, what is the pressure at which the combustion takes place or the constant pressure, into the final volume after the products are formed minus the initial volume when the reactant is initially present. U equal to U2 minus U1. Now, I write this as Q equal to P delta V plus delta U, which is nothing but delta H, that is H2 minus H1. This is the enthalpy of the products and this is the enthalpy of the reactants, and this I call the heat of reaction. So, in a constant pressure process, heat of reaction is nothing but the change in enthalpy. Enthalpy of the product minus enthalpy reaction reactants, and since Hp is actually less than Hr, you know that is less than 0. That is, heat is rejected to the surroundings. Okay, so that is what I have written here. Delta Hr is negative, heat is transferred from the system to the surroundings. Now, we have seen about the adiabatic flame temperature. So, if you try to insulate your piston cylinder arrangement, then the products will reach the maximum temperature, which is the adiabatic flame temperature. Now, we will go on to the reaction at the constant volume condition, like in a bomb colorimeter, rigid vessel. So, reaction occurs from reactant to the products. Now, for this there is no change in volume. So, W equal to integral P dV equal to 0. So, we have Q equal to delta U, which is nothing but the internal energy of the products minus the internal energy of the reactants. The measurement of internal energy has several uncertainties. Internal energy basically is a disorderly nature of energy due to the microscopic, it is called microscopic form of energy. So, generally enthalpy can be measured more accurately, and from that we determine the internal energy using the definition of enthalpy. So, here the internal energy of the products is written as Hp, that is the enthalpy of the products. We know how to find the enthalpy of products because enthalpy of product is nothing but the sigma Ni H bar I of the product stream. For example, not product stream, not product stream, it's just products in this case because there is no flow. When you have a system, there is no flow. So, once final products are formed, say if there are n product species, then Ni Hi bar, that will be the absolute enthalpy or standard enthalpy. You know how to find it. So, to recall this quickly, this is nothing but H F of I, that is the enthalpy formation, plus sensible enthalpy at a particular temperature. Okay, so how to find Hp? Use this. Similarly, Hr you can use this. Individual enthalpies you will find at the given temperature and use this. Then you know the final temperature of the products because the constant volume vessel, as temperature increases, you can use PV equal to mRT. Okay, and you can find that since V is constant, as T increases, P will increase. So, that will be the final pressure of the product. Initial pressure of the reactant is PR. V is constant, so P into V. So you can calculate this, or you can invoke PV equal to NR UT, that is universal gas constant, and find the internal energy of the product as HP, the enthalpy of the product mixture, minus number of moles of the product mixture NP into RU into TP, and so on. So in the constant volume case, there is no work interaction, and the internal energy change contributes to delta HR. The heat of reaction is nothing but the change in the internal energy, the internal energy of the product minus the internal energy of the reactant. In the case of constant pressure reaction, it is HP minus HR, that is the change in the enthalpy. So let us consider a constant volume combustor and try to evaluate a pressure rise in this, considering C3H6 and 150% theoretical air present at standard conditions, 100 kilopascals, 298 Kelvin. So you have a vessel in which you have the mixture of C3H6 plus 150% theoretical air, stoichiometric air. Now the mixture is ignited and complete combustion takes place. What we do is I allow for heat transfer. When I do that, I maintain the temperature inside the rigid container as 1200 Kelvin. Okay, so if I don't do the heat transfer, then what happens? The temperature may rise beyond 1200 Kelvin. So what I do is let the mixture be ignited, complete combustion takes place, and let the heat be transferred so that the temperature of the product is maintained at 1200. Now how to analyze this? Let us take the chemical reaction. C3H6 plus 6.75 O2 plus 3.76 N2. Okay, so this 6.75 is 150 times the stoichiometric air required. So complete combustion takes place, that means 3 kilomoles of CO2, 3 kilomoles of H2O form, and the excess oxygen, that is 2.25 moles, will appear in the products, plus all the nitrogen 3.76 into 6.75 remain as inert. This is what usually we write. So now how to find the final pressure? Please understand that since the temperature is 1200, and even if you take the reactant side, the pressure is very low. So high pressures, low temperatures, you have high density. There we cannot invoke equation of state, which is ideal gas equation of state. We have to use real gas equation of states. But since the temperature is higher or pressure is lower in the initial and final conditions, we can invoke ideal gas equation of state. That is PV equal to NRUT. Okay, so that is the advantage of combustion calculations. Now we have already seen that the state 1 initially is that of the reactant, then finally it becomes products. It's an irreversible process. Once the products are formed, we cannot get back the reactants. So number of moles of the reactant N1 or NR, what we can say is 1 plus 6.75 into 4.76. This will be 1 plus 6.75 into 4.76. Similarly, the number of moles of the products N2 or NP will be equal to 3 plus 3 plus 2.25 plus 25.38. That's it. So now it's very simple, just use the equation of state and calculate what is the equation of PV equal to NRUT, but V is constant. So we can say P2 by P1 will be equal to N2 T2 divided by N1 T1, and you know all the number of moles and temperatures, etc. So you can see that P2 will be equal to approximately 4 times the initial pressure, 408.76 kilopascals. So, this is what happens in explosion vessels, etc., where the previous combustion is studied. So, pressure rise. So, if the temperature is maintained as say higher temperature, then the pressure will still increase beyond this value and so on. So, this is a way to calculate the constant volume combustion, pressure rise and so on. Now, we can calculate the heat of reaction also from this. What is that? Enthalpy of the reactants, products minus the enthalpy of the reactants, and you have to use the equation of state. It is actually UP minus UR. Delta HR, if you want to calculate, it will be UP minus UR. That we can write as HP minus HR plus you have to have what? NPRU TP minus NRRU TP. So, this is the way you calculate the delta HR for this. So, that is what we are trying to do now. Heat of reaction Q equal to U2 minus U1, that is H2 minus N2 RU T2 minus H1 minus N1 RU T1. So, H1 is nothing but, since the reactants are at 298 Kelvin, H1 will be nothing but the enthalpy of formation of propene only. So, that you take from the tables. Now, enthalpy of products H2 will be 3 times CO2, 3 times enthalpy of formation of CO2 plus the sensible enthalpy of CO2, delta H CO2, as its temperature increases from 298 Kelvin to 1200, plus 3 times enthalpy of formation of water vapor plus delta H H2O 1200. Okay, the temperature increases. For the O2 and N2, only sensible enthalpies are involved. There is no enthalpy of formation, they are basic elements. So, take the values from NIST database and substitute to get the value of H2. Now, what is Q? Will be H2 minus N2 RU. Please understand, this is 10 power minus 3 is to convert into kilojoules, because 8314 8.14, this is kilojoule per kilomole Kelvin. So, this 10 power minus 3 is used as a conversion factor from mole to kilomole, and 1200 is the temperature of the products, minus this is the enthalpy of the reactant minus NRRUT. So, that will be the value of the Q. Okay. Now, what will be the adiabatic flame temperature in this case? Adiabatic flame temperature, how will you find in for constant volume process? Adiabatic flame temperature is got by equating UP equal to UR, because you know that Q equal to U2 minus U1. If Q equal to 0, then U2 will be equal to U1, that will be UP equal to UR. Now, the adiabatic flame temperature got from a constant pressure process. So, you have the same reactants in a constant pressure process and constant volume process. When you try to insulate these two and try to calculate the adiabatic flame temperature, you will find that the adiabatic flame temperature, say Tp, for constant volume process will be greater than the adiabatic flame temperature for the constant pressure process. This is because in the constant pressure process there is some work interaction, some amount of energy goes on doing this work, but in the constant volume process there is no work interaction. Okay. So, this covers the first law, that is the calculation of heat of reaction and temperature. Now, let us see some basics of chemical kinetics. Okay. So, in the chemical kinetics, what we try to do is evaluate the rate at which a reaction takes place. So, the rate of the reaction, that is when there is a given amount of fuel and oxidizer, what will be the rate of the reaction? That actually depends upon two things. One is the temperature at which the, so how much temperature you put to initiate this, plus the concentration of the reaction. That is when the reaction takes place, the concentration of the reactant decrease. So if the initial concentration is high, then the reaction will take place at a faster rate, and the reaction rate obviously slows down as the concentration of the reactant decrease. Okay, now first of all, we have to classify the reactions and then understand what is the reaction rate. So, we have already seen something called global reaction, which is nothing but the overall reaction where the fuel which is used, oxidizer which is used, and the major products which are formed are listed. So, this is the overall or a global chemical reaction where methane and air at stoichiometric proportions are going to react to form complete products of combustion. But you can write this and calculate the heat of reaction. It will be this reaction is enough for us to calculate the heat of reaction, no issue. But to calculate temperature itself, we have seen that it is not possible for us to calculate the temperature, the maximum temperature accurately when you have only the major products CO2 and H2O and consider no dissociation. What happens? You predict 200 Kelvin, 300 Kelvin more than the possible or measured temperature. So, this global reaction which gives the idea about what are the reactants and what are the major products is quite useful for finding the heat of reaction. But to calculate temperature itself, we have seen that we need more number of species in the product side to evaluate the temperature more accurately. This is one particular point. Second is, this reaction cannot occur at one single step. Even though it is written as this, it cannot occur. Basically, we can say that a global reaction is molar reaction. What is molar reaction? We write this in terms of kilomoles of the species. 1 kilomole of methane reacts with 2 kilomoles of O2 and forms 1 kilomole of CO2 and 2 kilomoles of H2O. So, that is the way we read this reaction, what we have written here. So, number of moles. So, it is a molar reaction. Global reaction is a molar reaction. That means in 1 mole, several molecules are going to be present. But when the reaction really occurs, it is between 2 molecules only. So, when the 2 molecules hit, say for example, CH4 hits with the wall of a reactor or some other species, then it splits into CH3 plus H. So, you please understand that this is a molecular level reaction. One molecule of CH4 dissociates to form CH3 plus H. That is the molecular level reaction. But here only a global reaction, molar reaction is given. Obviously, this cannot take place in one step. Okay, so then what happens? The global reaction takes place in several steps, which are part of a chain reaction. The chain reaction has 4 stages. Okay, what happens in the first stage? The first stage is called chain initiation step, where the reactants are first disintegrated. As I told you, CH4 giving CH3 plus H, something like this. Similarly, O2 giving O plus O, and so on. And here this O and H will form to sorry react to form OH. So these are molecular level reactions. Okay, the initiation step is nothing but the reactants break and form radicals like OOH etc. HOOH. So these are called radicals which are highly reactive. Free bonds they have, so they are highly reactive. Okay, so that is the chain initiation step. These are molecular level reactions. So when I read this, I will say one molecule of CH4 breaks to form one molecule of CH3 plus one atom of hydrogen. Similarly, one molecule of O2 breaks to form two atoms of O. One atom of oxygen plus one atom of hydrogen forms one molecule of OH. So that is the way I read this. The previous case I told 1 kilomole of or 1 mole of methane reacts with 2 moles etc. That is molar. Global is a molar level reaction. So the radicals OH and OH are highly reactive. Now the second stage of the reaction will be chain propagation. So once the chain is initiated, it has to propagate. So a specific kind of species are formed here. Say for example H2O2 etc. Metastable species. These species are stable sometimes and unstable sometimes. So they are called metastable species. And again some amount of radicals are also formed. Okay. Again the chain propagation reactions are set of molecular level reactions. I will show you that later. The third stage is called chain branching. The reaction has to accelerate. So once some amount of radicals are built, then the radicals are also consumed. Okay, so this production and consumption of radicals will also cause more radicals to form. If the radicals are formed at a faster level, then those reactions are called chain branching reactions, in which in these reactions the overall reaction rate accelerates. Multiple radicals are formed. Finally, once the concentration of the reactants reduce and the final products are formed, a set of reactions called chain termination reaction will occur. That is the final fourth stage. Okay, here the final products are formed. But even though we have segregated this into 4 stages, all these stages will occur simultaneously. And what are the reactions which are going to be present in this? They are called elementary reactions, that is molecular level. Global reaction is a molar level, elementary reaction is a molecular level reaction. And you can see that in the global reaction we have put only one arrow, reactants giving products. But in these cases we will put two arrows, basically forward and backward arrows, to represent that they are reversible reactions. Okay, so this is another important set of reactions which we will see. So I will give a few examples of elementary reactions in this. As I told you, O2 to form two atoms of O plus O. This is the initiation step, where here M is called third body. Third body is nothing but the set of other species or wall where this particular species collide and break. Similarly, you will see that O2 plus CH4, the reactant species basically, break to form HO2. The HO2 also is a metastable species. CH3 also is like that. So again CH3 forms CH4 forms CH3 plus H, CH3 will form CH2 plus H and so on. So these are several sets. I am giving only one simple examples here. Several initiation steps will be there. Now you can see O is formed, H is formed here. So then OH will be formed. That is when radicals react to form more radicals, like H plus O to form O plus 2 radicals are formed here, branching. That means when multiple radicals are formed or only radicals are formed, then they are called branching reactions. They actually take place at faster rate and also aid in accelerating the overall reaction rate. Then propagation reaction. These are sets of that, where you will see that radical is formed, some amount of metastable things are formed. Okay, so metastable species plus radical is formed. Here metastable species is formed, and here radical is formed, and so on. So this means you will see that the equations what we have written are molecular equations, and several of these equations. So we can say that for methane we can define around 300 to 400 reactions like this, elementary reactions, to completely define the overall reaction mechanism. Then finally I have the termination, where H and OH combine to form the water vapor, CO plus O to form CO2, etc., where you see that the final products are formed, radicals are consumed. When radicals are consumed, the reaction goes to a termination. So this is the important thing which you should understand. There are two set of reactions. One is global reaction, which will not occur in one step, but it's only representative of the what are the reactants and what are all the products. And in order the actual reactions take place in molecular level through a set of elementary reactions which are displayed in this, which contribute to 4 stages of a chain reaction.